Hello everyone, welcome to my channel, MV's channel, where we'll be calculating some rather difficult intervals. This channel will present various techniques, all very important for calculating intervals, often definite intervals. We'll also be able to evaluate series, and we'll even see numbers of very important theorems about special functions. The aim of this channel is not to show you how I calculate these intervals, but to show you how you can have the reasoning that leads to the solution. In this way, you should be able to use these techniques yourself. You'll be able to progress in interval calculus, and from time to time I will calculate very difficult intervals that require very situational techniques. You will never get this kind of intervals in a calculus exam, but often the techniques used are techniques that you should be able to use yourself. The theorems about special functions are so important that you need to know them or be able to find them. This presentation has gone on long enough, so I hope you learned something from these videos, and in any case, I hope you have a good time watching a mathnet calculating crazy intervals. Now we can move on to what you clicked on, the tutorial for using the Feynman technique. This video covers the two cases where this technique is used, with some fairly easy examples to show you how it's done. Make sure you stay until the end of the video, because we're going to use Feynman's technique to calculate an antiderivative of a function, and I doubt that you've seen it often elsewhere. These techniques will be detailed once, and in the next few videos we'll go over them quickly. It's up to you to practice using it yourself, because it's going to come up a lot on this channel, as on all the YouTube channels that talk about integration. Feynman's technique is based on a very simple rule, which is a Leibniz rule, which says that to calculate the definite interval of a parametric function, differentiating outside the interval is the same as differentiating inside it. The only condition is that the function defined by the interval is from class C1, which is equivalent as the function inside of the interval is a continuous function. That means that if you're integrating a continuous function that depends on two variables, you can differentiate inside or outside the interval sign, and this won't change the value of the interval. The theorems says that d by ds, the interval from a to b of f x dx equals the interval from a to b of del by del s f of sx dx. And this very simple rule is extremely useful for simplifying all kinds of interval, because rather than calculating the interval we are given, we can introduce an additional parameter that change the function we're integrating, and it can greatly simplifies the calculation. It's a bit complicated to explain clearly how this technique works, but we're going to apply it to the simplest possible example, the interval from 1 to e of log x. And you will see it's not as mysterious as it sounds. Let's start by naming our 1 to e of log x dx. So first we have to name our interval so that we have something to refer to. Let's say we just call it I, and we can of course calculate this interval in another way by guessing an antiderivative. if you know an antiderivative of log x, for example, x times log x minus 1 plus c, that doesn't matter for definite intervals, you take the value of this antiderivative in e minus the value in 1, and you have the value of this interval. But if we want to use Feynman's technique, we can do things differently. We must pose a general case that allows us to find our particular interval. What is the problem here? The fact that we don't know an easy antiderivative of log x. We need to determine a parametric interval which, once differentiated, would produce a log x. So del by del s f of s x equals something times log x, and the something for some particular case s must be equal to 1. This is the general case, but you can have also something like this, and this have to be equal to 0, or, well, the easiest case is this one, and this here equals 1. Okay, how do we go about this? Well, it's easy. We have to take x to a variable power. If we take x to the s, when differentiating with respect to s, we get x to the s times log x. And if we say that s equals 0, we have just log x. So now we can do it. We can put I of s equals the interval with the same limits. So the interval from 1 to e of x to the s power dx. This interval is fairly easy to do since we integrate with respect to x. So the s here is just a constant. However, we only need to differentiate once and take the special case s equals 0 to find our more difficult interval. So let's do this. Our general interval is I of s, and by differentiation we have I prime of s equals d by ds, the interval from 1 to e, x to the s power dx, which is, according to Leibniz rule, equal to the interval from 1 to e of del by del s x to the s power dx. Since we differentiate with respect to the power and the base is a constant, we obtain x to the s power log x. Taking s equals 0, we get our interval I. This means I prime of 0 equals I, the interval we're looking for. So now let's calculate the general case I of s. We have the interval from 1 to e of x to the s power dx, which we calculate in this way. Since s is a constant for the interval and we need the case s equals 0, we can just assume that s is greater than -1, which means that we can use the general formula. The interval of x to the s power dx equals x to the s plus 1 power divided by s plus 1 plus capital C. And this function has to be taken between 1 and e. So I of s equals x to the s plus 1 power by s plus 1. We can just forget our plus c constant, taken between 1 to e, 1 and e, which is e to the s plus 1 power minus 1, all divided by s plus 1. Now we have to differentiate using the quotient rule, and we have that I prime of s equals e to the power of s plus 1 times s plus 1 minus e to the s plus 1 power minus 1 times 1. And all that is divided by s plus 1 squared. Okay, and this simplifies. Now we have I prime of s equals s e to the s plus 1 plus 1 all divided by s plus 1 squared. If we take our particular case s equals 0, we know I prime alpha. Okay, now you can see I prime of 0 equals, here we have e to the first power times 0 plus 1 divided by 1 squared, which is 1. And this is to be expected since it is easy to prove by classical techniques like IBP that this integral is indeed 1. Strictly speaking, this is not Feynman's technique. In fact, even Feynman's technique was not invented by Feynman, but he popularized it after his teacher showed him how to use it, and well, he used it to solve a multitude of very practical integrals in physics. This technique is a bit more subtle. It consists of posing a generalized integral, then differentiate the integral before calculating it, then taking the entire derivative, and finally taking our particular case. This technique requires more imagination than the previous one. The canonical example is the integral from 0 to 1 of x minus 1 by log x dx. The technique used last time won't work here. We'd have to come up with an example of function that's simpler to integrate, and then when we differentiate it, we get x minus 1 divided by log x. But, well, it's impossible to make divided by log x appear when differentiating. And I exclude the idea of making compound logarithms appear in the initial function because the aim of this generalization is to make the integral easier to calculate, and that can't be easier to calculate if you make compound logs appear, especially when integrating from 0 to 1, because compound logs mean that you have a complex valued function to integrate, so just forget it. Which this means our integral is, well, almost unsolvable with Leibniz rule. However, if we differentiate it a first time, taking inspiration from what we did last time, we might be able to make this log disappear, and the integral would become much simpler. So let's give it a try. We name this integral again I, and we let I of s being, well, the integral from 0 to 1 of x to the s power minus 1 by log x dx. Well, I prime of s would be the integral from 0 to 1 of del by del s x to the s power minus 1 by log x dx, which is the integral from 0 to 1 of x to the s power times log x by log x dx. We obtain 1 divided by s plus 1. We now have a general expression for I prime of s, 1 by s plus 1, and we can integrate in order to get back our I of s. I of s equals the integral, not the integral, I mean, equals log s plus 1. But wait, here we have our expression I prime of s, which is 1 by s plus 1. And now we're taking the entire derivative to get back I of s. But, well, we're not doing a definite interval. We're taking an entire derivative, which means we have to make sure that there is no plus c constant. So we have an expression for I prime of s, and we try to figure out an expression for I of s. Well, so this is the formula for our general interval, and we need to find a way to get the value of this constant c. How can we do that? We have to fix our value s to a value that is, well, easy calculated using this method to isolate our plus c, and with this method to get some value to our interval. And the easiest case, the one we can calculate without even know the entire derivative of this function, is the case s equals 0. Because in that way, we have here x to the 0th power, which is 1, so 1 minus 1 by log x, which is 0. Which means that we're integrating 0 over the segment 0, 1, which is of course 0. So I of 0 equals 0. And we know that I of 0, that's why we need this formula, log of 0 plus 1 plus capital C. And this equals 0, which leads to the conclusion C equals 0. Which means I of s equals log s plus 1. Now we can take the value we were looking for, s equals 1, and determine the value of the interval I equals I of 1 equals log 2. And well, as you can see, this technique is more complicated to use than Leibniz rule, but it can help to solve very difficult intervals without it. So it's important to master both. These two cases are intervals where it is easy to see how introducing a variable can help us to use one or other of the techniques. However, in many cases, it is not at all obvious. A classic example is the Dirichlet interval, which is the interval from 0 to infinity of sine x divided by x. The function is continuous on R, so we can use Leibniz rule, but with an unexpected factor. I'm not going to spoil anything from you, because I may solve this interval one day. Just be aware that trying to put the variable s inside the sine won't work, unless you consider that the interval from 0 to infinity of cosine x is exactly 0, which isn't totally absurd, but it would be a bit cavalier. But well, even if you do that, you won't be able to integrate your function properly and you will get stuck. So I advise you to practice these techniques yourself, as YouTube videos alone won't improve your intuition much. And maybe one day we'll meet again to solve this Dirichlet interval. Okay, and now, as promised, we're going to use Leibniz rule to calculate an entire derivative. This seems a bit absurd, since the aim of Leibniz rule is precisely to use bounds to fix our interval. And it's true, strictly speaking, it's not possible to use Leibniz rule without having fixed bounds, unless you use Leibniz complete rule, but well, it's useful when the bounds themselves depend on the second variable, not the variable of integration. So that's not what we're trying to do here. We can solve this problem with a little manipulation. we have to write the entire derivative as a definite integral, but with variable bounds. Take the example of the function log x. Well, we can just let I of x being the integral of log x dx. But we can also say that this equals the integral from anywhere to x log t dt, let's say from 0 to x. And now we can introduce our second variable s. So we pose I of x s being the integral from 0 to x of t, be careful, t to the s power dt. Well, we can differentiate under the integral sign, so if we say, we know that our function here, I of x, not I of s, we know that our function here, I of x, equals the derivative of I x s. And here by derivative, I mean with respect to s, and where here s equals 0. So, well, this is a bit more complicated than usual Lyman tool, but well, it's doable. Okay, we have to solve our generalized integral I of xs. So I of xs is this integral, and well, we can just integrate with respect to t, and we get t to the s plus 1 divided by s plus 1. Taken between 0 and x, which is x to the s plus 1 divided by s plus 1. And now we have to differentiate with respect to s, so del by del s I of xs equals, so we use again the quotient rule, and we have x to the s plus 1 power log x s plus 1 minus x to the s plus 1 power divided by s plus 1 squared. So letting s equal 0, getting gives us x to the first power log x times 1 minus x divided by 1 squared, which is x log x minus x. And here we don't have a constant plus c because we're doing an integral from 0 to x, not a simple entire derivative calculation. So here is our integral. If you really want, you can just add here an extra plus c, but well, it's not even necessary because here we know that this is I of x, which is the integral from 0 to x of log t dt. So this is kind of a definite integral. Now you see, this is how we can evaluate an entire derivative using Lyman tool. I hope you've understood the operations I've performed. If you're having trouble with either of these two techniques, check out Black Pen Red Pen's channel, where he gives a good explanation of how to use them. You'll find everything on his channel, but especially indefinite integrals. On Flammable Math channel, you'll find more definite integrals and generally a bit more difficult integrals, like Ahmed integral and Coxeter integral. I hope you've learned something, and well, if you have any comments on the video or the text, please give me some advice on how to improve the videos. That's what the comment section is for. See you in the next video for the integral from 0 to infinity to positive infinity of log x log 1 plus x squared divided by x squared dx. This is an integral of medium difficulty, I think, so try it yourself before watching the video. It's a pretty fun integral, in my opinion, because it can be solved in 100 different ways. Like, we have a Leibniz rule, Feynman's technique, we have different Leibniz rule and Feynman's technique to use on the same integral, and we even have complex analysis and more. So I know, I think, like 7 different ways to calculating it, and there are probably more, so try it yourself, and well, until then, study, learn, and progress.